Okay, so here I've got all the relevant equilibria for the acidic forms at least. So for each of these, there's a Ka value. We have pKa1, pKa2, pKa3 with their associated values. And let's consider now 0.1 molar solution of each species. What's the pH? Okay, so to start with, we can consider 0.1 molar phosphoric acid. Well, this is just going to be Ka1 is equal to x squared over f minus x, which means we'll have 10 to the negative 2.148, this value of pKa1, is equal to x squared over 0.1 minus x. We can go ahead and solve this. I'm skipping all the algebra involved here, but we get x equals 0.0233 molar, and remember x is equal to the concentration of H+. So that gives us a pH of 1.63, which is what we'd expect. We get an acidic pH for the acidic form. All right, and so this is just using the same approach that we use for any other weak acid, for a monoprotic weak acid. Next, we can consider 0.1 molar phosphate. We'll do the other one that's like a monoprotic system. Here now we use Kb1, which is equal to Kw over Ka3. So that'll be equal to 1 times 10 to the minus 14 over 10 to the negative 12.375. Again, that'll be equal to x squared over f here being 0.1 minus x. We can plug all those values in, and we'll get x equals 2.61 times 10 to the minus, x equals 0.0383. Sorry, I was looking ahead. Molar. And remember, this is the concentration of hydroxide. We could find the POH to find the pH, or you can use Kw to find H+. Right, so if we use Kw, we get H+ equals Kw over concentration of hydroxide. 1 times 10 to the minus 14 divided by 0.0383, which gives us a very small concentration of H+, which we'd expect because this is a base. 2.61 times 10 to the negative 13. We convert that to a pH and we get 12.58. So very basic, like we'd expect. Now the intermediate forms, we can use the equations that the equation that we have previously derived. All right, so 0.1 molar H2PO4 minus. So that's the 1 proton lost. We can use concentration of H+ is going to be equal to the square root of all this stuff. Right. So we'll have K1 and K2, and in this case that's Ka1 and Ka2. So we'll have, I've got those calculated out here instead of the 10 to the, from their pKa values. We have 7.11 times 10 to the minus 3 times, just trying to read my notes over here, 6.34 times 10 to the minus 8 times our concentration, 0.01, plus 7.11 times 10 to the minus 3 times Kw, 1.0 times 10 to the minus 14. All of that divided by 7.11 times 10 to the minus 3 again, plus 0.10. So we can plug all that into the calculator. We get a value of 2.05 times 10 to the minus 5 molar, which gives a pH of 4.69. So a little bit acidic, as we would expect. This is the doubly protonated species still. And then the final one we could do is 0.1 molar HPO42 minus hydrogen phosphate. And we use this same equation, but now our K1 and K2 values are different. So now our K1 is Ka2, which is 6.34 times 10 to the minus 8. And our K2 is Ka3, which we can calculate out as 4.22 times 10 to the minus 13. And then this will be times 0.1 plus 6.34 times 10 to the minus 8 times Kw. This is an 8 up here. Divided by 6.34 times 10 to the minus 8 plus 0.1. All right, we plug all that in. We get a value of 1.82 times 10 to the minus 10 molar. And if we plug that into the pH equation, we get a pH of 9.74. Okay, and now we get something that's a little bit basic, whereas here we've got something that was a little bit acidic, which is what we'd expect based on the Ka values for phosphoric acid. All right, but as you can see, once we have these equations, we have sort of the similar setup. No matter which acid we're looking at, what's going to change is the K values. But otherwise, it's fairly straightforward. The key is keeping track. Right here, we need to use, for HPO42 minus, we need to use Ka2 and Ka3, whereas for H2, for dihydrogen phosphate, here we had to use Ka1 and Ka2. But that's an example of how we can apply this to a polyprotic system. That we could extend this, of course, to other acids and bases. Just keeping track of whether it's the fully protonated form. For the fully protonated form, we treat it as a monoprotic weak acid. For the fully deprotonated form, treat it as a monoprotic weak base. And for these intermediate forms, we need to use this longer equation. Or I didn't show it, but you could use the even simpler approximation of 1/2 pKa1 times plus pKa2, 1/2 times that sum, like we did for the diprotic system. And you'll get something that's pretty close to what you'll get from these values, provided the assumptions that go into that equation hold true.